Hello, integrated science students. We're now going to cover a chapter on classical physics. And we'll begin by discussing the history of some very early developments in science to sort of see how science was done. And in doing so, we'll talk about people like Aristotle and Copernicus and Kepler and Galileo and, yes, Sir Isaac Newton. Let's begin by going way back to about 600 BC, or before the Common Era, to a person named Thales of Miletus. Now, Thales of Miletus was one of the first recorded scientists, or person who actually engaged in some type of scientific investigation. It is said, and it may be a little bit of mythology, that he was one of the first persons to predict a solar eclipse. It's said that Thales thought that all matter was made of water and that the earth was more or less a flat disk. And a couple of the big questions that we'll talk about as we go through some of these early scientists were whether or not the earth was spherical or flat or some other shape, and the question of whether or not the sun and the other planets, other things in the sky, revolved around the earth, or whether or not the earth revolves around the sun, that is the structure of our solar system. Following Thales, there were other early scientists, Anaximander and Anaximenes, but we don't have time to talk about everyone, so let's go to another important person named Pythagoras. You may have heard of the Pythagorean theorem if you've had courses in mathematics. No, we're not going to cover that exactly right now. But Pythagoras was a mathematician, lived in the southern part of Italy, and he created a school of mathematics, and he considered the circle and the sphere to be perfect shapes. In fact, he thought that the earth was round. And he also thought that the earth revolved around the sun. And so he more or less had it right. And that was about 550 BC. Then along comes other natural philosophers. One of the most important one is Aristotle, who lived between 384 and 322 BC. Now, Aristotle proposed what we call the geocentric model of the universe. That is, that the earth was the center. Now, why did he think this? Well, he was actually influenced by other earlier natural philosophers, one of which was named Empedocles. Now, Empedocles, if you've heard of the earth, air, fire, and water model for the basic elements, Empedocles likely came up with the first description of the earth, air, fire, and water model. And according to this model, which Aristotle endorsed, earth was the heaviest of these four elements. And so logically, if it were the heaviest, it would sink to the center. Then, according to Aristotle and others, the earth would be the center because everything was sinking towards the center. And then water was on the surface of the earth as both lakes and rivers and oceans and rain and clouds. And then above that, we would have other layers of fire and air, and that there were concentric circles beyond that, which is illustrated in this drawing. This sort of illustrates Aristotle's view of the universe, of everything. That is, there were concentric spheres with the earth at the center. Then you would have the moon, Luna, Mercury, Venus, Sun, Solus, Mars, Jupiter, Saturn, and then the other celestial objects, the stars. So this is Aristotle's model. There's some logic to it. That is, if Earth is the heaviest of these elements, it would sink towards the center. And then you would have everything else to the outer layers. Now, Aristotle actually came up with another element called ether as an explanation for how these stars and the other planets could exist out in these other concentric layers. What was holding them there? And he considered that to be the fifth element called the ether. So Aristotle had some interesting ideas. Many of them turned out not to be right, but one idea that he had that was correct, of course, was that the earth was round. Another important person that comes along is Claudius Ptolemy. Now, Ptolemy was an astronomer, but he also was sort of a librarian. He not only made his own astronomical observations, but he collected those of others and wrote a number of books. And he lived in about the 2nd century AD. Now, after Ptolemy's death, it turns out that there was a lot of havoc. There was a lot of fighting among people, and his library and his books were essentially destroyed, except for one copy that was sort of spirited away and was safely stored in a monastery outside of what is now Baghdad. And it turns out that when Baghdad was built in about the 8th century, this collection of books, that the one that had been safely stored, books by Ptolemy, was discovered. And then Ptolemy's books were translated into Arabic and preserved in what became called the Almagest, which is translated to the greatest collection of these scientific books about the heavens. As the story continues, the Muslims in North Africa at some point in the 8th century then invaded Spain and occupied part of Spain for a number of centuries. And so the Almagest was then brought to Europe and was translated into Latin. And the story then goes that Columbus used these astronomical books from Ptolemy to help guide his travels as he sailed towards the Indies, which are to the North American continent. But the more important story is that this geocentric model for the solar system, for the universe, proposed by Aristotle and then written down for posterity by Claudius Ptolemy, dominated our thinking for as much as 1,500 years before scientists began asking questions. And among those people who asked the questions were people like Copernicus and Kepler, because even though the geocentric model was widely endorsed, it was taught in all the schools and universities, and it was supported by the church, there were still some nagging problems. One of these was what is called the retrograde motion of the planets. That is, if you observe the planets like Mars and Jupiter, it was found that they didn't follow nice regular patterns, but they did loop-de-loops every once in a while. And so how would they explain this retrograde patterns? So this shows you an example of the retrograde motion of Mars. Well, it was a minor problem. Copernicus then came along the scene around 1500, and he was an astronomer. He was in Poland, and he studied the motion of various planets, and he thought, let me see, I think there can be another explanation besides the Earth being the center of the solar system. Maybe the sun, that big object in the sky, the sun, is the center of the solar system. And he came up with his model. Now, his model we call the heliocentric or sun-centered model for the solar system, with the planets encircling the sun in circular orbits and the moon circling the Earth. Now, his model still did not explain this retrograde motion, but it harkened back to some of the very early natural philosophers, Pythagoras, with the sun being the center of the motion of the solar system. Now, Copernicus was a little reluctant to publish this for fear of the church authorities, but on his deathbed he published a book called On the Revolution of Heavenly Spheres. Then a little later, another astronomer, Johannes Kepler, came on the scene. Kepler lived in Germany. He was a mathematician and an astronomer as well. And he considered Copernicus's works, and he came up with the analysis that the orbits of the planets around the sun, that yes, the sun is the center, the heliocentric model, but instead of being perfect circles, they are ellipses. They're oval-shaped. And that secondly, that the planets, that in this oval shape, sometimes they'll be closer to the sun and sometimes further away. And he predicted that when they were closer, they sped up and moved more rapidly, and when they were further away, they moved more slowly. So one of these kind of things. And he also came up with an analysis showing that the period, you can think of that as the year, the time, that is the length of time it would take for a planet to go completely around the sun in one complete revolution. That period, if you square it and divide by the distance between the sun and the planet, cubed, or p squared divided by d cubed, that this ratio is the same for all planets in the solar system. That is, Kepler is developing a more scientific model for the solar system. And then the next important natural philosopher or scientist who comes on the scene is Galileo Galilei in Italy. The previous astronomers, Copernicus and Kepler, are observing these heavenly bodies with their naked eye. But Galileo develops a telescope, which enables him to see these heavenly bodies much more clearly. His observation supported the heliocentric model of the solar system, that is, the sun being the center. He also studied the moon and Jupiter and actually discovered that Jupiter has moons itself. And he wrote a book in 1610 called The Starry Messenger. It's also true, and you may have heard, that he got into some trouble with the church because the church had sort of banned a book written by Copernicus. And here Galileo in Italy, well known to the people in the Vatican, was promoting this heliocentric model, which the church thought was heresy, and so they sort of told him not to talk about this. And he wrote another interesting book, which maybe you'll hear about. But nevertheless, he made some very important contributions to science. Now, not only in astronomy, he made some very important contributions, not only in astronomy, but also in what we call classical mechanics, that is, the study of moving objects. For example, we show on this slide an inclined plane with an object like a ball rolling down the plane. And you'll notice that it shows the position of this object after 1 second, and 2 seconds, and 3 seconds, and 4 seconds, and 5 seconds. And notice that the distance traveled increases with each increment of time. Okay, this is one of the important observations made by Galileo, that things seem to speed up, that under the influence of some acceleration. Now, what's this acceleration due to? Well, it's due to gravity, and we'll be talking in one of the next video lectures about gravity. Now, there is a story, it may be a myth, about Galileo dropping 2 balls from the Leaning Tower of Pisa. Have you heard about this? And he essentially did this to refute Aristotle's teachings. Remember, Aristotle said that there are heavier objects would fall towards the center, and an extension of that was that heavier objects would fall faster than lighter objects. Galileo went to the top of the Leaning Tower of Pisa, took 2 objects, both round, about the same size and shape, but one much heavier than the other, like a bowling ball and a soccer ball, maybe. So he drops them from the Leaning Tower of Pisa, and they both hit the ground at the same time. So this refuted the principle of Aristotle, and it says that things are a little bit more interesting, a little bit more complicated than that. It's not just the heavier things fall faster. Now, some equations that Galileo and others have developed, which will be important for you to have a little bit of understanding of, are shown in the left of this slide. Velocity. Velocity, the speed at which something moves in a particular direction. Now, velocity is actually something we call a vector. It has both speed and direction. So we can talk about a speed going south or north or up or down. That is, velocity has a direction, whereas speed just has a speed. So let's say that we are driving our car and we're traveling 60 miles in 1 hour. Okay? That's a velocity. 60 miles is the distance, d. 1 hour is the time, t. So the distance divided by the time is the velocity, v. Velocity equals distance divided by time. So if we know the velocity we're going and we know the length of time, we can multiply velocity times time to get distance. Or if we know the distance we've traveled in a particular time at a constant velocity or constant speed, we can use that to calculate our velocity. Now, another important equation is the second one shown here. Velocity is equal to an acceleration times time. Now, this applies if an object starts at rest and then experiences a constant acceleration. Now, what would be a constant acceleration? Well, you've heard of, you have this car and it goes from a standstill to 60 miles per hour in so many seconds. You've heard people talk about that. Well, that might be a constant acceleration. But the constant acceleration that is most common to us is the acceleration of gravity. And we'll talk more about this. But if an object, such as the ones that our friend Galileo dropped from the Leaning Tower of Pisa, Initially, he has them at rest. He's holding them up at the top of this tower. They're not moving. And he drops them, and they undergo acceleration due to gravity. The velocity that they're falling is equal to the product of the acceleration of gravity times time. Now, in other words, and this is what is shown in that inclined plane above, the velocity will increase with time. Okay, velocity will increase with time when you drop an object. The third equation is more of a practical equation, that is, and it combines the above two, and it says if you want to calculate the distance traveled for an object that experiences a constant acceleration, again like an object we drop from the top of the Leaning Tower of Pisa, that the distance that it travels is equal to 1/2 times that acceleration times time squared, whatever the time is squared. Or if we know the distance that the object is going to travel and we know what the acceleration value is, we can calculate the time. So we can either calculate the distance or the time that it would take for the object to fall, whatever distance it's falling. That is an application of the way we use that equation. So these are some of the equations that Galileo knew. And Galileo died in 1642. And the same year that Galileo died, in England, a child was born, Isaac Newton. And so we'll pause now, and when we continue, we'll talk about Isaac Newton and his contributions. Okay, see you shortly.